Poiseuille's law says that the flow, so Poiseuille, okay, well, I'm going to just write it down. Q is proportional to delta P, right? Or Q is proportional to delta P over L, pressure gradient. And that would look like a line. And you could plot flow, volume flow rate, versus, this isn't pulsatile flow again, we're moving on to turbulence. So the volume flow rate versus pressure difference in a tube would follow a straight line if you were using Poiseuille's law. But Poiseuille's law won't go on forever. At some point, you might be trying to put too much flow, too much pressure difference, and things don't act linearly. And so when you have streamlined flow, Poiseuille's law is going to work, and it's going to follow a straight line. If you try to push that fluid too quickly by putting too large of a pressure difference, there'll be sort of a breakdown in streamlined flow, and you're going to have a petering out of your flow, okay? So you might want to try to double that flow rate by doubling your pressure difference, and you won't get it, okay? You see, like if we try to double from here on, you double that flow the pressure difference, you would have thought you would be getting double your flow. You don't get it, okay? It's less, okay? So that's what we go on to next. Why is it less? Because you start getting turbulence. It's very similar, this curve, to the plastic deformation, right? I mean, it just looks the same, right? So you had elastic deformation, and then it moved on to plastic deformation. A very similar type of curve. You've got a linear relationship when you have streamlined flow. As soon as you start getting turbulence, which is a rolling action, everything breaks down, and you start losing that really nice linear relationship. So we're not going to calculate out what that curve does, but what we do want to know is when can you expect this onset of turbulence flow, okay? So, okay. So once you have turbulence, you get a waste of energy, okay? And that energy can be in the form of heat or noise. So like if you go into, well, I would have said go to the basement of the physics building, and you'd hear all of the noise of the gas flowing through the pipes, because they're obviously passing too much fluid too quickly, and the pipes are shaking above your head. It's noisy. So that means that there's a waste of energy going on in the form of noise, and you can actually even create heat. So if you're trying to push too much fluid too quickly, and you start getting into the turbulent regime, then you're actually could even be heating things up. I remember I was working once in a lab at Cornell, and we had this big accelerator, and the accelerator was particle accelerator. So we were accelerating electrons and positrons and colliding them. And so I was working in the lab, and my lab was right next door to the water circulation system that was cooling down this accelerator. And as I was working, I just noticed that day after day, month after week, the water cooling system was just getting louder and louder. And later on, it just got better. And I asked, well, what happened? Why did the sound get so much better? It was so loud, I couldn't concentrate. We got a new technician a new scientist in charge of the cooling system, they said. So, well, what did he do? Well, what happened was, this is the story, is that the previous guy was trying to solve the heating problem in the accelerator, and he wasn't keeping up with the demand of the accelerator, and he kept on putting in pumps that were putting more pressure through the lines to try to get that cooling water into the accelerator. And it was getting worse and worse. And he kept on putting bigger and bigger and bigger pumps, which were louder and louder. And the problem was only getting worse. And finally, someone figured this out, and they got rid of him, put in a new guy. The new guy looked and said, hey, your pumps are pumping so much water through these pipes that you're actually heating the water, okay, because of turbulence. And so he replaced these massive pumps with this tiny little quiet pump that was just flowing the liquid in a streamlined laminar flow. The place was quiet and the accelerator got cooler. So very simple first year physics concept that the first guy who lost his job because of it didn't realize is that if you push too much water too quickly through pipes, you'll actually be heating up your water, and it will counterproductive. Okay, that's a tough story. So energy can be lost, okay, if you try to push too much fluid through a tube too quickly. When you have turbulence, Bernoulli's equation is not valid. Poiseuille's law is not valid. You're not in the linear regime. But of course, the equation of continuity is still valid. That's always true. That's saying that the flow is equal to the area times the velocity. Okay, that one always holds. But it's good to know these points. That's a very easy multiple choice question. You can imagine. Move on. Now we're going to move on to something quantitative. Some over 100 years ago, this guy Reynolds came up with this mathematical way of trying to predict things, and it worked. So his question was, is it possible to calculate whether flow will be turbulent or not? And his answer was maybe, sort of. But he attacked it in a mathematical way, and he got somewhere. It's named after him. So you've got the tube, and there's going to be the diameter of the tube, the density of the fluid, the viscosity of the fluid, and the average flow rate. And these are going to be the parameters that are needed to understand the problem. What Reynolds figured out was, okay, he created a ratio of those numbers, those values. The density times the diameter times the velocity average divided by the viscosity, and he got a number. And it turns out the units all cancel out if you use the proper units, and you get a number. That's it. And it's called the Reynolds number. Okay, so what do you do with the Reynolds number? Well, do you know you use the Reynolds number? Let's see what happens. The Reynolds number is, well, you can read more about it. Move on. This is the point. That if you get a Reynolds number that's less than 2,000, it's going to be streamlined flow. If that number is higher than 16,000, it's definitely going to be turbulent flow. There's going to be this intermediate region between 2,000 and 16,000 where we're going to say probably turbulent, or eventually it's going to become turbulent. Okay? And that's how it is. Why? Because what happens is if you have the fluid flowing through a pipe and it's going less than 2,000, you're sure it's going to be non-turbulent. It's going to be laminar flow. Bernoulli's equation or Poiseuille's equation, depending, is going to work. If you start pushing that fluid too quickly and you get into this regime where you're higher than 2,000, it could start off as laminar flow, but eventually there's going to be like a little hiccup, and that's going to cause a little vortex, and that vortex is going to create more vortices, and you're going to have this turbulent flow occur, and it's just a matter of time. It's sort of like if you're driving in a car through Mississauga, and you notice that we're all going really quickly on this highway, and you ask yourself, you get a good drivers start get a sense like, we've got too much velocity here for too big a congestion. This can't this can't hold on forever. And eventually what happens is one car swerves, makes a little mistake, and that causes a chain reaction. And next thing you know it, someone has to stop. The next guy or girl has to stop even harder, and you have a traffic jam. Okay? And so, when you push things beyond the limit, eventually there's a breakdown. That's what this 2,000 to 16,000 regime is like. You can get away with it for a while, but eventually you're going to probably get turbulence. Okay, so let's do an example. And this is an interesting example. A water pump generates a constant flow, Q, which is currently causing a turbulent spray with a Reynolds number of 32,000 out of the cylindrical nozzle. Which of the following three nozzles could be substituted to achieve a streamlined flow with a Reynolds number less than 2,000? So this is a comparison problem where they didn't really tell us what the diameter was. They just call it D. Okay. All of the lengths of these are going to be the same. Okay. We're going to try to figure out which one of these have turbulence or not. Okay. So let me open up an empty page.